Why does electronics hiss, even when you're doing everything right? You short the input, you shield the cables, you power it from a clean supply, yet the oscilloscope still shows a fuzzy baseline. So why does noise exist at all? Because at any temperature above absolute zero, electric charge carriers are always jiggling randomly. That microscopic motion turns into a measurable voltage that you can't turn off. A plain resistor, one of the simplest components ever invented, literally generates its own noise just by being warm. Thermal noise is the sound of heat showing up as randomness in electricity. Inside a conductor, electrons don't glide smoothly like cars on a highway. They behave more like a crowd in a busy hallway, constantly bumping, scattering, and changing direction. The warmer the material is, the more energy those particles have, and the more chaotic their motion becomes. That chaos doesn't produce a steady DC offset, it produces tiny, constantly changing fluctuations, up, down, like a coin flip happening billions of times per second. This is called Johnson-Nyquist noise, and it's one of the most fundamental limits in electronics. The important idea isn't the formula, it's what the formula says: the noise grows with temperature, and it grows with bandwidth, how wide a range of frequencies you're listening to. Think of bandwidth like the width of a window. If you open the window wider, you let in more sound from outside. In electronics, a wider bandwidth means you're collecting more random fluctuations, so the measured noise increases. That's why changing a measurement setting can change the noise you see. On an oscilloscope, if you limit bandwidth, the trace often looks thinner and calmer. Nothing magical happened inside the resistor. You just stopped listening to the higher frequency parts of the randomness. The noise didn't disappear, it simply moved outside the range you chose to observe. Engineers do this on purpose all the time. They design filters so the circuit only pays attention to the frequencies that matter and ignores the rest. Temperature is the next lever. Lower the temperature, lower the thermal motion, lower the noise. That's one reason high-end scientific instruments and some radio astronomy receivers use cooling, sometimes extreme cooling. It's not for drama. It's because when you're trying to detect a signal that's unbelievably faint, thermal noise becomes the loudest thing in the room. Cool the system, and the room gets quieter. Then there's resistance. Higher resistance generally means more thermal noise voltage. Again, don't memorize it. Understand the intuition. A resistor is a place where moving charges experience collisions and randomness. If your circuit uses very large resistances, the noise voltage you can measure across them tends to be larger. That doesn't mean resistors are bad. It means every design choice has a cost. High resistance can save power, but it can also raise the noise floor. Now here's the part people get wrong. Shielding won't remove thermal noise. Shielding blocks external interference, radio signals, power line hum, electromagnetic junk floating through the air. But thermal noise is born inside the component. You can put a resistor in a perfect Faraday cage and it will still generate noise because the source isn't outside. It's the physics of temperature and charge. And this matters everywhere. It's why low-light photos look grainy, why audio gear has a hiss at high gain, and why deep space communication is so hard, because the signal arriving at the antenna can be smaller than the random fluctuations produced by the receiver itself. Engineering, in many cases, is the art of pulling a meaningful pattern out of unavoidable randomness. So noise exists because heat makes charge carriers move randomly, and anytime you measure a real circuit, you're measuring that motion too. Now the next question: why does digital audio and digital video still have noise if it's all ones and zeros?